what we did before the Christmas break, essentially for like 5 or 6 weeks, we talked about data encryption standard and AES, and then we talked about modes of operation. And I think I told you now we're done with symmetric ciphers. But then I was going back and forth, and I talked with Dejan a lot, and we thought, no, there are two important subjects that are really hard to get somewhere else, and that belong to symmetric cryptography, in particular block ciphers, and I do want to do them today. So today there will be one more lectures where we do talk about symmetric cryptography, and really two topics we're going to discuss, namely the topic of multiple encryption, which we split in double encryption and triple encryption. And there's a pretty good results that we see today. So it's pretty surprising. It's not too mathematical, but it's a pretty nifty trick, a pretty cool trick that we're going to introduce with double encryption. A pretty surprising fact of block ciphers. And then the third part of the lecture, we want to go back to brute force attacks. We didn't really explain what brute force attacks are about. And again, we will learn something new, how to do brute force attacks, and there's another surprising result which comes as news. So I think it's a pretty cool selection of topics today. I think it's hopefully a pretty interesting lecture. So the first section or chapter of today will deal with double encryption. Colon, Doppelpunkt, and more specifically, double encryption takes about 1 minute to explain. What we really want to show, what I really want to show you, to make a long story short, that double encryption is a stupid idea. And why is that? Because there's an attack which is specific to double encryption, which is called the meet in the middle attack. So what this section really is about is this new attack. So this is the headline of the first chapter, is the meet in the middle attack. Okay, so the way this is usually motivated, so much of the material today is motivated by the use of DES. Okay, this is an old cipher, but it has some very, very nice properties, and it's still widely used. And motivation that we have here is using of DES, which is basically a sound cipher. Does anyone know what's the meaning of sound here? So this is now English 101, okay, or English 501. Does anyone know what sound means here in this sound cipher? You know, we know sound as in acoustics. Sound is also the German word gesund. You know, sound, gesund, right? So sound cipher is a gesunder cipher. So this is a solid, good cipher. Okay, so it's good English. Okay, using of DES basically a sound cipher. And what is the problem with DES? Why is it still, we should not use standard DES. What is the problem with DES? There's one sentence answer. What is the problem with DES? Yeah, key lengths, exactly. But key space is too small. Okay, so the problem with DES is this here, right? You have DES. And unfortunately, we only have 56 key bits. And as you saw in the first lecture, you can build, for about 10,000 euros in material cost, you can build a key breaker which breaks DES within a few days. And you know, for 100,000 euros, you can break it in a day or so. Okay, so, but DES is very nice. First of all, there are a lot of in particular hardware products out there that use DES, and but also, particularly if you put it in hardware such as the e-passport that is used in Germany and also worldwide, that is employing DES, but then it doesn't work. So the question is, it has very nice hardware properties. How can we how can we make DES stronger? Okay, and the main idea is that we're not encrypting once with DES, but we try to encrypt with DES once and a second time. Okay, and this is called double encryption. So the idea, and this is not, rocket science, as they say, double encrypt. So encrypt, instead of encrypting once, encrypt twice. And now, so if you're copying, you have to watch out. Don't make the drawing, your figure you're drawing here, make it here. I would say at least 10 Kästchen, okay? 5 centimeters, 10 little squares, okay? You see that here, and that's too narrow. 10 Kästchen at least, okay? So what's going to be here, this is what you're going to draw here in the next 15 minutes is going to be the most important part of the lecture, okay? So we encrypt with DES, and instead of DES, I write E because this is easier to write. You go in with X, and you get Y out, and we introduce an index here, so we go in with X1, and the results, the ciphertext, we call Y1. And of course, the main idea why we're doing that, if you encrypt twice, you also deal with 2 keys, right? So we call this the left key, K sub L, and this becomes the right key, K sub R. And of course, each key has 56 bits. Okay. So, and now the I think I go here. So, question is here complexity of brute force attack. So how complex is it to brute force attack that baby? And the idea is the naive approach is I might have talked about that, right? If you want to have really fancy English, naive gets 2 dots. It's very strange they don't tell you that. This is if you write really good English, you write it with 2 dots. Okay, most people don't, but this is really good English. Okay, so the naive approach is that you do it as follows. You take Y1 and you decrypt. You go back this way, you jump over this cipher. That means you're running through all K, call them KJ, KJ, K sub J, okay. So you're going back to here, and then you decrypt again. I call it K sub I. Oh, sorry, this is all decryption, right? So, okay. And what you have to check, so we decrypted this once, we decrypted this twice, and now we have to check, is this result equal to X1? Okay? Everybody with me? So very simple way of running a brute force attack. So what is the complexity here is, how many keys Ki are here? How many keys KL do we have? How many key tests do we have to check here? How many keys are there? What's the key space at this point? Yeah, to the 56, right? But for every key that you check here, you also have to check every key here, and you have to, unfortunately, to multiply this. So this is, you run through, let's say you fix a 0 key here, you run to the 56 keys, okay? Then you increment, hochzählen, right? You increment this ki, and again you run to the 56 keys. You increment here, you again run through them. So altogether you get 256 times, this times is going to play a role, mal, right? Times 2 to the 56, which is, okay. So this is key tests. Okay, this is if you want to do that, this is lifetime of the universe or something, right? Two to the 112 is a very, very large number. If you start doing that with all computers that we have on Earth right now, the sun will cool down and blah, 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 blah. Okay, 2 to the 112 is really large. You will not succeed. So from looking at that, it looks like a really great idea. Just encrypt twice and you get something very secure. But as often in cryptography, things are very tricky. And there's a very nice attack, named the meet in the middle attack, which we're going to introduce now. And also, by the way, you have to wake up at this point in time. So the next 10 minutes are the essence of today's lecture. Please be awake, don't talk, don't do YouTube, whatever, okay? Just listen. Okay, so now what is the idea? So the question is, can we find a better attack? And the answer is yes, we can, okay? And what is the idea, kind of in a very abstract, the very abstract thought behind this is, question here, can we search for KL and KR separately? Right now we're not searching separately. We fix KL and then we run through all KRs, and then we increment KL and we run through all KRs. So this is really, we have to combine them. The idea is if we find an attack where we can first check all KLs and then we're done with that, and then we check for all KRs, we get the following complexity. So if this is possible, we would have 2 to the 56. So this would be search for KL. And then the idea is, can we search for that without touching the right key? Only search the key space of the left key. And once we're done with that, we also have to search for KR. If this works, and of course that's a big if this works, we don't have a multiply, we have a times here, and there's a big difference because this becomes 2 times 2 to the 56, which is 2 to the 57. That means this is hardly more secure than normal disk. So it's almost the same security, right? Just a factor 2. And factor 2 is, you search like 2 days or 4 days, right? This is still, it doesn't get you much extra security. So the big question is, of course, how can we do that? How can we search separately? That means first we want to run through all KLs, and then we want to run through all KRs. And this is the meet in the middle attack. So how does this work? So this is kind of a very basic thought, and now we try to build an actual attack, come up with an algorithm, with a method to get this behavior. Okay. The idea is I think I switched to colors. The idea is so what we're going to do now is the yet now the actual attack comes meet in the middle attack. Okay. So the first thing that we're doing, which we call, there's a two-phase attack. And two phases make sense. Phase 1 is looking for the left key. Phase 2 is going to look for the right key. Okay. So what we do in phase 1 is essentially running a standard brute force attacks against the left side of the encryption. So search through all K1. And if you do that, you know, if you take K1 equal to 0, KL equal 0, 1, 2, 3, 4, blah, 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 up to 2 to the 56, if you do that, you know, you never know when you have the right key. So what we do instead means we start running through all KLs here. Okay, that means we're going this way. So you encrypt KL of x1. And the interesting thing is, at this point, you don't know whether you have the right key KL, because you're only looking at the left-hand side. But what we do, we run through all keys here, and we store we store all the values in the middle. Everything that we compute here, we call that Z or Z. So this is ZL, right? And this we put in a large table, in a large database. Okay, so we compute at this point. We start compute a table, and the entries of the table, and now it's getting a little bit messy, bisschen unordentlich with the indexes, with the indices here. So we have more than one KL, right? So, you know, 0, 1, 2, 3, up to 2 to the 56 minus 1. So we do that comma I here as well. So this is ZL comma E, right? Comma I in German. And what you put in this table is those pairs. That means you put in ZL comma I, and on the other side of the same record gets the, let's say this is what you compute with the all 0 key. Okay, so this is KL 56 zeros, 0, 0, 0, 0, 0. Then you increment and you get the next one, and this would be ZL comma 2 with the key KL comma 1, I'm sorry, comma 1 with the key 0, 0, 0, 0, 0, 0, 1. Okay, and you increase it like a counter, wie ein Tacho, right? You run 0, 0, 0, 1, 2, 3, 4. You run through all values. And the very last key that you're testing is the key KL sub 2 to the 56 minus 1. What is the bit pattern? What's this bit muster of this key here? How does this look? How do the 56 bits look? They're all ones, right? 1, 1, if you know this is 56 bits, you have 1, 1, 1, 1, 1, 1, 1, right? It's the end of your counter, okay? And then for this key, if you encrypt x1, you get a certain z value, ZL comma 2 to the 56 minus 1, okay? Sort through all K1, and store intermediate values. ZL, okay? Okay. So the question is, what is the complexity of this phase one type of the attack? Complexity. How many encryptions do we have to do here? What is the effort here? How many different keys do we have here? Yeah. Exactly. This is one normal death brute force attack, right? So this is 2 to the 56 encryptions. But are these the only costs, or is there anything else we have to do? You see it on the blackboard. What else do we have to do? What are the other costs of this part of the attack? What else do we have to do? Yeah. You have to store it, right? And this is a lot of hard disk space, right? 2 to the 56 bits, and they're fairly large, the number of bits you have to store, plus 2 to the 56 storage locations, I call that, okay? Per location, you have to store. What do we have to store? Well, you have to store 64 bits here, so 8 bytes of ciphertext, and 56 bits. That means 7 bytes of keys. So you have to store 15 bytes per location. But this is a detail. We leave that out. Okay. So we just say we have 2 to the 56 storage locations. It's a pretty large table. You need a fair amount of money to buy that hard disk space, okay? But it can be done, it's not the budget of Germany or something, right? It's probably a few millions or so. You can do that. Okay, so that was part one, and right now we haven't learned anything. Okay, if you only do phase one, this is stupid. You can't do anything with that, right? We do have nicely tabulated those 2 to the 56 intermediate values in the middle here. We don't know what to do. So now in order to break the cipher, the second phase comes in. The first phase is coming from the left. That was the deal. We don't have loudspeakers, I'm sorry. We're coming from the left, going into the middle. The second phase is coming from the right and going to the middle, and somehow try to find some matching values. That's the idea. Meet in the middle attack, right? Meet in the middle attack. This is coming from left, phase one. Phase two, different color, goes this way. Okay. And what do we do in phase two? Be careful with copying here. So you start from the other side. So you can't do encryption, you have to do decryption because we go in this direction, right? We go from ciphertext to plain text. That means you decrypt, right? E to the -1, which is our symbol for decryption today. You decrypt Y1, and with which key are you searching for? You run through all keys KR. So we call this KR, J. K index L, J, K sub R, J. And we call this intermediate value, we give it a name, we call it ZR, J. Okay? So this is now, let's write that down. This is now phase two. compute the following, namely, and this is just the formula we have up there, Z sub R comma J, also ZRJ, is equal to the decrypted version of our ciphertext, Y1, and the key gets as the name KR, J. And so what are the possible values for the key that we are having? Well, the key is just as before. You start with 0, with 1, and potentially, right, the largest value that you can check for is again this, 56 ones. This is the worst thing that can happen, okay? So this is the basic idea. So and now comes the thing where you really kind of the gist, the main idea of the attack. What are we looking for? So let's start from the beginning. So the first key that we're checking is all zeros, 56 zeros at this point. You decrypt Y1, you end up with this value, right? This Z value here. And what are we looking for now? If you do the first, what do we do with this Z value here? Any ideas? Yeah? We're looking for a matching value. Wir gucken uns einen Wert, wir gucken, ob das in der Tabelle ist. So we're looking whether this value is in the table. Okay? The chances are you don't succeed with the first value. Okay, so what do we do? Well, you increment, you go to 1. So the value here is now 0. Before it was 0, 0, 0, 0, 0, 0. Now you do 0, 0, 0, 0, 0, 1. Okay, you pick the next key, you decrypt, you get a new ZR value here, ZR, comma 1. You look whether it's in the table. Probably it's not the second key you're checking for, right? You would be really lucky. So we increment again, we take the third key, you get the third Z value, you again look in the table. And you do that and do that and do that. And at some point, you must find a Z value that is in this table. Okay? So you check for what you call matching, and I call collision, but matching is just as good. What we're doing here is now, for every ZR, comma J, check for what we call a collision, i.e., das heißt, i.e., is, what do we mean by collision? Is there a value ZL, comma I such that, so dass, this is the collision so that the value in the table is equal to this value we just computed. And you have to, every time you have to look through the whole table, but searching through ordered tables is pretty quick. Okay. So this is what we call a collision. That means the value that we computed here is already in the table, somewhere in the middle typically, right? It's not the first or the second or the last one, somewhere in the middle. And why is that a really cool thing? What happens? If we have such a collision, what do we know? Once we have this collision here, that means if this collision condition is fulfilled, what we know is, and I'm going backwards, so I start with Y1 here, I take Y1 and I decrypt it. Using this key from the collision here, okay? So this is the it's this key that belongs to, let's say, to this R, really. So it's the same J value, okay? This is the key that gave me the collision here from the right-hand side, okay? The key I just tested. And then I see the collision somewhere in the table, right? This ZLI, I called it, and somewhere here. And this Z value comes together with the K value, right? You have a key that belongs to this Z value. So what I do, I take this key, again, sorry, I'm jumping back and forth. So and I decrypt it this way. Now I have an index for a key here, and I decrypt again, and what I get out is the X1 I want. So when I decrypt this here, again, and this time I'm taking the left key out of the table. This is the key that helped me create the collision. So this LE here is this here. Again, you decrypt this whole shebang here. If you do that, you decrypt once, you decrypt twice, what you get out is X1. Okay. So what does this mean? Well, this is the left key. That's the key we were looking for. And that's the right key we are looking for. We found the two correct keys here. So what happens now, once we have this, we as attacker, we essentially won. We won the fight. We found the keys we were looking for, hopefully. KL1, KRJ, sorry, KLI, KRJ. That were used in the collision. Maybe let's give that. That's a very important equation here. I get this equation, which is kind of the key equation, gets number 1 in the collision here. Are possible keys. And actually, in the case of death, with very high likelihood, these keys are exactly the keys we are looking for. KL, KR. Okay. One thing that can happen, and this will be the last part of the lecture today, is you can have matches. That means you can have you can go back here, with a certain key here, find a collision here, find a match here with a certain key here, and this works. So this equation holds. Okay? Y1 decrypt again, you get X1 out. Everything is fine, but it can still be the wrong key. Okay, the wrong keys. Okay, they are, and why is that? Because sometimes it's very weird, and this will be the last part of the lecture. Sometimes you can have multiple keys that compute X1, Y1 here. This is weird behavior. We're going to talk about that in whatever 20 minutes or so. Okay, but with in the case if you use DES here, not another block cipher, if you use actually DES, with very high likelihood, the keys you found here, the keys that you used at this point, and this key, and that gave you the collision, are the actual keys KL, KR. Okay? It's no big deal if there's a wrong keys. There's a very easy test for doing that. Okay. Note. or remark. Okay, sometimes we have to use a second pair x2, y2. That means you need here at this point and getting y's is not a problem. As an attacker, you have y anyway, but you need you have to know a second input block here, a second known plain text. And with the second block, you again check, is this left key that you found and the right key you found from your collision search, from your meet in the middle attack, do they also work correctly with x2 and y2? And if they work correctly with very high likelihood, now you finally have the correct keys. Does anyone know what happens if this doesn't work? So if those keys don't do this decryption correctly, does anyone know what we have to do with the attack in this case? You continue with phase 2. Means you found one collision here, and that gave you what we call a false positive key. So what happens is, if this second check fails, you say, well, this is not the right key, that wasn't the right collision. You keep searching through KR here, okay? And at some point you will find the next collision. At some point you have to find the right collision here, okay? So the big thing now to finish this meet in the middle attack is the total Gesamt complexity. Phase 1, we saw this as 2 to the 56 encryptions plus 2 to the 56 storage. Können wir ruhig sein? Danke. And phase 2, what is the worst case for phase 2? What is the worst thing we have to do? The largest number of computations, what is that? What is the worst case here until we find a collision? Yeah? Exactly. You know, I've written it down here. If you're really bad luck, you have to test all possible keys before you find your first collision, but you have to find it. So the worst case of phase 2 is, again, and then you sum that up, and now it's exactly what's happening. You know, you have to add the complexities. You don't multiply the complexities. You first do this attack, this brute force attack, this search, and then you do the second search. And totally, if 2 to the 56 plus 2 to the 56 is 2 to the 57 plus storage. And the morale of the story, right, the conclusion is double encryption is only marginally, so Marge ist Kante grenzwertig, also ist nur ein kleines bisschen, marginally more secure than single encryption. And that's the first part of the lecture. What we really did in the last 40 minutes is don't do double encryption. It's stupid, okay? Yeah. Okay. gute Frage, auch gutes in Deutsch. So the question is, in number 2, we have, you have to check for this. That means you have to go in the table, and this is not for free, right? Does anyone know what the complexity of table lookup is? Haben Sie das in Informatik gemacht schon? Sortieralgorithmen. Was will ich hier hören? Wer ist die Komplexität? Wenn die auch wieder, wenn Sie hier auch wieder 256, könnten wir es einstampfen. Weil dann hätten wir hier 256 Schritte und wenn wir jetzt pro Schritt wieder 2 hoch 56 Einträge hätten, wäre das Ding ein Schrott. Ne? Aber Logarithmus. Das hängt damit zusammen. So what you have to do, I do that in English again, it's good for the video. You have to sort the table by the z values here. So we're not sorting by k, so this is 0, 0, 0. They're sorted by the z values here. Okay? Sie sortieren nach den z-Einträgen und dann können Sie mit 56 Schritten sind Sie da. Das ist wie im Telefonbuch. It's the same with a phone book. If you have a phone book, you're pretty quick with finding a number, right? And this is because it's sorted by the alphabet, right? I don't know whether you noticed that, right? They were, start with A and ends at Z. If I give you the phone book of a big city of Bochum or so, and it's unsorted, let's say with 100,000 entries, you would have a complexity of 100,000, right? You have to check every entry. If it's sorted, wenn es geordnet ist, you get a logarithmic complexity here. Very good remark. But what this really means is the search is not slow, the sorting costs. Yeah? Okay, was a good remark. So this is approximately. Was a very good remark. Ja, andere Frage. X1, X2, yeah? Yeah, yeah. Yeah. Yeah, no, no, it's only the probability. And we do that, this is the last part of the lecture today, and I give you the probability, and you get down to 2 to the minus 100 or so. But this method definitely finds the right key. Okay, okay, good. So, again, I think this is a very cool thing, and this is the reason, and many people in industry, software engineers, they always see triple death, and they don't, why don't we do double death? You already get twice the key length, it seems. It's because of this attack. So that's why we did that today. So the question is, what do we do instead? Surprise, surprise, double encryption doesn't work. Let's try the next thing that we can do. Let's try triple encryption. Again, 10 little squares, space, okay, 10 Kästchen freilassen. At least 10 Kästchen, okay. So what we do now is now we need 3 keys. Okay. So now if you're the good guy, if you're Alice or Bob and you want to encrypt, you get your plain text, and you have to encrypt once, you have to encrypt twice, you have to encrypt a third time. Okay, using three different keys. They're kind of variants, but let's say in a simple case you actually use 3 different keys. So what everybody in this room, all 100 people should do if they see that said, oh, bad idea, Professor Paar just showed us this really cool attack here, right? Meet in the middle. Well, we can meet in the middle here again. Okay, so what we can do, of course, we can try to run this attack. That means we go from here, and I'm not torturing you with all the ugly notations here. You start computing a table here, right? And what you have to do at this point here, you run through all k1s, okay? So if you actually start, and this is meet in the middle attack, you can do that, right? So we do phase 1. And this is just the complexity we saw before. This is the yellow part of everything that's on these blackboards here, right? So again, 2 to the 56 encryptions plus 2 to the 56 storage elements. Okay, so far so good. The problem starts with phase 2. What you would like to do is to do something like this, okay? So you jump over this last block. And what is the complexity here? It's again, I'm sorry, this is all 56 bits, yeah? If you do this, and we can do that, this would be 2 to the 56, this would be 2 to the 56. The problem at this point, you can't find a collision here, right? Everybody with me? Now you would have a table at this point, but where do we want to end up? We don't want to end up here. We want to end up here, right? You have to jump not over 1 block, but over 2 blocks, okay? And you can do that. You can do that. But what is the problem here if you do this jump and jump? What is the complexity of that here? How many possibilities are here? Yeah, 2 to the 112, they multiply, that's the problem. You know, here you have to run through all possibilities of K1 and K3 combined, right? You can't do first K3 and then K2, that doesn't work. So what you have to do at this point here you have to K2, comma J, and here you have to decrypt Y1, K3, comma L, I call that, right? If you do that, so this would become phase 2. The problem here is this is 2 to the 56 times 2 to the 56 encryptions, okay? In total, this becomes 2 to the 56 plus 2 to the 112 encryptions, and this is roughly 2 to the 112 encryptions. Okay. So what's the strange thing about that is that triple encryption, right? We encrypt 1, 2, 3 times. So the effort for the good guy, for Alice and Bob, or for your passport, right? Whoever has a modern German passport, or I think they're also in the German ID card, Deutsche Personalausweis, that's the new one that's out there. They actually use triple DES. So the effort for your passport is 1, 2, 3, right? You have 3 times the workload for encryption. The security that you get is roughly what we would expect from double encryption, right? You get the double key length, you do 3 times the work, okay? So, because you have with triple encryption, the best attack, which is this attack, which is meet in the middle, that's a good attack. It's much, much better than the normal brute force would be 2 to the so naive, if you do this naively, (150 und 18, 168, right? So the naive attack would be that, okay? So this is an improvement, right? You by a factor 2 to the 56 faster. This is really great. Unfortunately, doing 2 to the 112 is completely out of reach, right? It's again lifetime of the universe, blah, 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 okay? The important conclusion of this is called, in the case of DES, this is called triple DES, and it's often used this notation, right? The number 3 DES, triple DES, okay? Triple DES has an effective key length. So we talk about an effective key length, die effektive, die wirksame, die tatsächliche key length of 112 bits. Okay. That means in security terms, you have a key length of 112 bits. In work terms, you know, if you encrypt, of course, you actually you need 3 keys here, right? You need 168 key bits, but the security level is 112. But 112 is absolutely sufficient, okay? Again, this is why people put that in modern passports, right? Year 2011, right? Newly designed passport schemes use that with this strength. This is very, very secure. Ja, gute Frage. No, you can is 4, yeah, good question. Is 4 times any help here? What would happen with 4 times? In 4 times, the first phase of the attack would also go up to 2 to the 56, right? So you would have 2 to the 112 here and 2 to the 112 here, so that you wouldn't gain much. The next improvement is how often do we have to do that? 5 times. If you do 5 times, again, you can only meet in the middle once, right? If you have 5, 1, 2, 3, 4, 5, you can say, okay, meet after the second one, and this would be 112, but then here you have to jump over 1, 2, 3 blocks. This is 168. So we always go in chunk. But frankly, and I looked at many encryption schemes in my life and a lot of application, I've never seen people doing quadruple, you know, 5-fache Verschlüsselung. Good, excellent question. Another question was a, yeah. Yeah, yeah. I don't want to explain that here. It's right. Look in the book. Yeah, you can do that. Yeah. It only confuses people. So look in the book. Yeah. You can do that. Yeah. They're advanced attacks, and the most conservative, what he's really saying, you can play around with reusing certain keys and stuff. I think for now and for the videos and everything, this is good. Look in the book if you want to have more information. This is if you have the choice, do it this way, okay? There's also DES-X, which is a variant, and so forth. Any more questions at the moment? Yeah? Yeah, there's also particular for DES, this is standardized, this is encryption, decryption, encryption. You can do that too. Why is that? Then, particularly if you have hardware modules, little hardware chips, which is what's in our passports, in the new passports. There are some applications where you want to use single DES. Okay, if this is in hardware, you can't run single DES here. Okay, so this is really it's a good question. So you have a little hardware chips, that means you can't go inside, and then what people do, okay. If you do normal encryption, you do, in DES it doesn't matter, but you do encryption and decryption here. This works just as an encryption, so the same security claim. But does anyone know what do we have to do so that we effectively only use case 3? What can we do here? If you only would do, we have this is in hardware. That means you can't You cannot do this here, right? Yeah. Exactly. If you do this, you have a hardware module. The only thing you can do, you can feed in X 3 keys and Y, okay? In this scenario, if you choose K1, this is K1 and K2 also becomes K1, then what you do, you encrypt, you decrypt. That means these two operations cancel. Which value do we have at this point here? X. It's kind of a stupid thing, right? You encrypt and then you decrypt, but this is a little tiny hardware chip in your passport that does it for free, right? It's like 1 milliwatt or something you need for doing this operation. And then X is only encrypted once. That's why there are a lot of commercial solutions which do, and they call that encryption, decryption, encryption. So this is triple DES in EDE mode, EDE modus, okay? It's very advanced. It's not advanced, it's very applied, not very deep. It's very confusing for everyone, okay? There will be I don't think there will be any, will be on the final exam. Don't worry about that. But it's a good discussion here. Any more questions, or can I start with the third? Okay. So, this was chapter number 2. And now we're left with one chapter which really ties a lot of things together. In particular, what we want to explain is this behavior, which is every time I teach that is I have kind of, people can, I hope people can follow this here. I like this subject, I do this meet in the middle attack, the students follow, said, oh, this is a cool trick, and does this really work? Oh, I think I got the idea, it's a cool trick, right? And then when I lose people, I said, oh, Christof is a really bad teacher, is at this point, and suddenly I say, well, you can have bad luck. There can be keys, but they're not really the right keys, and you have to check X2 and YT, and why is that? And this is what I'm going to explain now to you. And this is, I think, there are hardly any crypto books that talk about that. It's not very difficult, it's hard to find. Okay, so be awake. Okay, so the third, so we want to talk about this phenomena of the wrong keys. Okay, you can do a brute force attack, and you find keys, and they do the encryption, decryption correctly, but they're not really the key that Alice and Bob used. Right? You're Oscar, you find a key, you encrypt X1, and Y1 comes out. You think you're there, but it's not really the right key. So you get this false positive results. Okay. This is, we do on this board, I think. Okay, so this is the, and I call the third chapter of today, I call that brute force attacks revisited. So the big problem is here exhaustive key searches. And by the way, exhaustive key search is the same as brute force. It's a fancier term, it's the same thing, okay? Whether we say brute force or exhaustive key search is the same, okay? Exhaustive key searches can give false positive results. Okay, that means if we have a block cipher here, and now it becomes more generic. Now it's not specific to DES, so you have your block cipher here. You go in with X1, you go out with Y1. You have a key, and we call the key KT for target key. So that's the real key that Alice and Bob is using. KT is target key. Okay. So this is Alice and Bob. This is how Alice and Bob computed, or let's say how Alice computed x1, computed y1. So x1 is the first, whatever, in the case of AES, the first 16 bytes of her email. Können wir noch? Hallo? Hallo? 20 Minuten, okay? 20 minutes? Can do that? If you're really tired by now, go to sleep, but don't talk, okay? This is perfectly fine with me, okay? This is what Alice did. So she uses the target key. Now the weird thing is what can happen is, what does false positive means? I think I write that down here. I.e., das heißt, Oscar, if Oscar finds this here, so he finds one key, and now the notation is not pretty today, right? Die Notation ist hässlich heute, yeah. So I have this K1 parenthesis, okay, K1. Sag ich mal gerade in Deutsch, und ich mache die Klammern, damit die Leute nicht denken, das ist K hoch 1 oder nachher K hoch 2, K hoch 3, deswegen macht man die in Klammern. Das ist keine Potenz. Und ich will nicht noch einen Index einführen, okay, das ist eine Alternative zum Index. Das ist K1, so this is K1, okay. So, Oscar finds this from his brute force attack, okay, and you don't do double encryption, triple encryption. Also works with the problem can happen with any block cipher. So this happens, but this K1 is not the target key. It's not the key that Alice and Bob use. So this is what Alice does. This is a real key. This is what Oscar does. He finds the key. It's the wrong key. Okay. So we give this equation becomes we had one before, so this becomes equation number 2. Okay. Likelihood of 2, that means the likelihood that this happens here with the wrong key depends on something very simple. Likelihood of 2 depends on the relative size, also relative Größe, Kardinalität, relative size of the key space, which I think, I don't know, I might have introduced that in the first lecture. Sometimes I introduce that, sometimes I don't, sometimes I forget. The key space, we use the calligraphic K, kalligraphisches K oder Schreibschrift. End of first grade, yeah. You know, normally you learn Druckschrift first and then you do handwriting, right? This is Schreibschrift, okay. So this is the key space, the calligraphic denotes the key space, and the 2 bars, die beiden Striche, ist Größe von Kardinalität. So this is, in the case of DES, this is 2 to the 56. The size of the key space and plain text space. Or plain text, ciphertext space, which is the same in block ciphers, which we call, again, kalligraphisches P with bars, okay? And now I promise the last time you have to wake up for 5 minutes, okay? So now I'm going to explain new theory to you. Let's do an example. And you should be awake at this point. You don't want to learn the stuff from the book that I'm explaining now. Be present, listen, stop talking. Just please listen for 5 minutes and the world will look very rosy, okay? You can do that on Sunday or probably next week, Monday night, but it will take you an hour or so to understand. It's 5 minutes if you pay attention, okay? It's just an offer. Okay, so the example is, we have to look at the relatively sizes here. We say, we assume a block cipher with an 80-bit key, so the key space is 2 to the 80. And there's some block ciphers that have 80 bits, so 80 bits is an interesting number in cryptography for whatever reason. But the block size is 64 bits, like this, and like many other ciphers. There are tons of ciphers that have actually a block size of 2 to the 64. Okay, so now let's draw a little diagram. This is the plain text space. This is this cloud here. You have 2 to the 64 dots in here, right? These are all possible plain text. And one of the possible plain text, let's say this here, is actually x1. Oh, I'm sorry. Okay, so this is x1. And now what we start doing, we start mapping that into the ciphertext space, calligraphic C. So this is all possible ciphertext. Many ciphertext, okay? So, and now it's a Gedankenexperiment. Pay attention. This is something the book can't really explain to you as nicely as I'm here, okay? So, you take x1, you start your brute force attack, you take the first key, you get some y value out. So this is k whatever, 0. What we really would like to do is we would like to land here. Okay, we know y1, probably you start with the first key. The odds are you're not hitting immediately the right y, right? You're somewhere else. So what do we do? Well, it's an exhaustive key search. We try the next key. You go here, and you might end up here at this point, right? So this is K1. Okay? You get the idea, right? The third one, and this is homework assignment. You do 2 to the 80 arrows, right? No, it's not homework. So at some point, this condition is fulfilled. At some point, yoo-hoo, we have a match, okay? That means at some point, we have the key K1, which maps to the same Y1, okay? The problem is, and now let's do a counting argument. We start with K0, K1. Let's assume this is the last key. That means we ran through, this would be, 2 to the 50. Don't copy that. I'm going to erase it. 2 to the 56. 2 to the 64. That means every time we pick a key, we get another spot here. Okay? And this is a random mapping. This is the thing here. Given x1, you randomly pick a point here in the ciphertext space. Okay? Now we're done after 264. Have we tried all possible keys? There are many more keys, and any key that you pick, every time you pick a key, you encrypt x1 with this key, you randomly, kind of close eyes, and you land here, right? And you do that over and over again, and you do that 2 to the 80 times, and the problem is 2 to the 80 times is much larger than this is. There are only 2 to the 64 entries, but you shoot in here, right? You randomly, it's like a dart. What's a dart spiel, right? With a file. You throw your dart 2 to the 80 times, so many, many, many more times, okay? That means at some point you exhausted all to the 64 points, but you still have billions and billions and billions of darts to throw, right? So what's going to happen here is you continue and you get a lot of wrong keys, but unfortunately, you get also a lot of correct keys. You get also K2 and a K3 and so forth, okay? And on average with these numbers here, there are 2 to the 80 mappings from the plain text space into the ciphertext space, okay? And, sorry, from x1 into the ciphertext space, right? This is what we're doing. We start with x1. Now, if the mappings select random elements from C, this is what I meant throwing a dart. What you do here, you randomly pick elements. This is what's happening. For a good block cipher, this is like a random permutation. This is a technical term here. Does anyone know how many false positive keys do we get? How many mappings onto Y1 do we get here? Does anyone has a feeling for that? They're all equally likely here. You get, this is, so these become, these are candidate keys. So number of key candidates. Again, has anyone an idea what the number might be here? Yeah. Almost. What it is we have 2 to the 80 keys here, right? And they equally, on average, each of these y, you know, there's all the yi's here, yj, and so forth. All the y's here are hit with an equal probability. So that means on average, going from x1, you have 2 to the 80 divided by 2 to the number of keys in total, 2 to the 16 keys here, okay? So this is the number, that means this would go down here, and here the last one that we have, that would have the index k to the 2 to the 16. What is that in decimal, 2 to the 16? What is 2 to the 6? Which number is 2 to the 16 if you punch that in your pocket calculator? Ungefähr, was ist 2 hoch 16? 65,000 something, right? So, we have 65,000 arrows here. Don't try to draw them at home, right? There are too many. Okay, so this is. Ja. Ja, kann sein, ja. Wir haben genau 1, aber es ist immer noch eine Wahrscheinlichkeit, dass es dann noch ein zweites gibt, weil der ist halt nicht so ganz richtig gut. Theoretisch kann es sein, ja klar, kann sein, genau. So, from here it seems, well, we find, it's a good remark, but it's really easy to get rid of that. Now from here, it seems it's kind of a stupid situation. So what do we do? The interesting thing is, now it's important. Yes. Note. You have 65,000 keys here. Interestingly, one of the keys is this key K sub t, right? One of the keys is the correct key. Okay, note. One key candidate is the target key. What does it mean? There is one of these keys here, right, that are circled with yellow. K sub I is the key I'm looking for, okay? And now comes really, I think, the intellectual hurdle of understanding this whole thing. What now happens is, idea, use second pair plaintext ciphertext. That means now we make use of x1, x2, y2, I'm sorry. Okay, so we're going. So it means at this point here, and now I should have written that down as an assumption. Our assumption slightly changes. Now we assume that Oscar does have a second key available. Not second key, a second non-plain text. Okay, this for 64 bits, 8 bytes. He not only knows 8 bytes, he knows 16 bytes. Okay, and what happens now? And I've never done that, what I'm going to do with you now, and I hope it works. So I change colors. You do the same game again, okay? You take x2, you use one key. No, I'm sorry. Not doing the same thing again. I never explained it. So what you're doing is you're taking K1, this K superscript 1, and you try to map that, okay? And you probably end up here. So you use K1 from here. Then you're using K2 from here, and you probably get wrong matches. The idea is now that what happens with the correct key here, with this K, somewhere this is KT. What happens if you pick the target key? The target key was used for mapping x2 by Alice to y2. So you run through all the keys, and at some point, you will use the Ki, and this Ki will land you here, okay? And then you know that you have the target key, okay? And why is that? Because for x2, y2, again, you get an ensemble, a set, a selection of 2 to the 16 keys that give you wrong positive results. Okay, if you would, which we don't do in practice, but x2 you can run through 2 to the 80 keys here. That means you get 2 to the 80 mappings, and many mappings go wrong, but again you get many correct mappings here. Are you with me? But what you would also get, you would get something like, you know what we use this yellow oval here. You would get the same here. You get you would get 2 to the 16 mappings from x2 to y2. Okay. Again, you get many false candidate keys. But what is special here? What is special about KT here at this point? I don't know whether that makes sense. This KT must be in this set of 65,000 keys, right? This target key, the real key. But the real key must also be part of these 65,000 keys here, okay? And the chances are, with these numbers that we have, that all the other, you know, let's say only there's somewhere here is the target key, right? This is, okay, target key, okay? The chances are that the target key is here, and no, not the chances are, it's 100% sure that the target key is here and here, but the chances are pretty low that that there's any of the other keys, any of the other 65,000 keys that is present in here and here. And now I give you the exact probability. So the question is, what is the chance that there's any of the other keys, any of the other false positive keys, that this is part of this ensemble and of this ensemble, okay? And what we need for that is just the notation changes here. Okay, so we have x1, x2, up to xt. That means we have t pairs. That's what the attacker has, okay? And now we need a notation. This is n bits in, n bits out, of course. This is key. And here I ran out of letters. I'm really sorry. I used the Greek kappa here, okay? I'm sorry. It's in the book. And that's, I got it from the literature, okay? So, if we have that, and now we're almost done with the course, with the lecture today. Now we have the theorem this theorem 5.2.1. Don't copy that, what I'm writing down here. You have it in the book, okay? It's a few lines of text, okay? Given a block cipher with a key length of kappa bits and block size n and t pairs of plain text ciphertext. I just abbreviate this. And now comes the important thing, and there will be problems, there will probably be exam problems on that formula here. The expected number of false keys is 2 to the kappa minus t times n. So we're almost done. Now let's look at our example with this theorem. 64-bit block size and 80-bit key. And now that's the question is, before we had the problem, if you have only one, if you have x1 and y1, you get 65,000 wrong keys, right? You get many false positive results. Now, what happens if we go to t equals 2? That means we have x1, x2, y1, y2. Okay, what is the likelihood that you still get a wrong key, a false key? Okay, well, the likelihood is, and you simply plug this in. This is like pre-university, so this is 80 bits minus, we have 2 pairs, and the block size is 64, so this is 2 to the 80 minus 128, so this is 2 to the minus 48. Okay. That means this is a very, very low number. You know, you find a key that encrypts x1 to y1 and x1 to y2. You could still have a false key, but it is a very high likelihood. If you say, well, this is not really good, right? I want to have something of higher quality. Then you go to 3 pairs. And what you get here ist 180, 192 und das ist 112, ne? Yeah. So with 3 pairs, you get this unbelievably small likelihood, okay? You can live with that, you know. It's much likely that the whatever, you win in the lotto every week for the rest of your life or something, right? This is not going to happen. So you see, we have very small numbers of plaintext ciphertext, and we get really, really low probabilities here. That means as soon as you have a few extra pairs, x and y, brute force attacks becomes very, very successful. Okay? Very good lecture. Thank you very much.